Welcome to e-learning. I am P. Saktivel, Assistant Professor, Department of EEE, Thandai Periyar Government Institute of Technology, Vellore. Today's topic, thyristor triggering. Triggering means turning on of a device from its off state. Thyristor is turned on by increasing the anode current. There are 5 types of triggerings: forward voltage triggering, thermal triggering, light triggering, dV by dt triggering, gate triggering. First one, forward voltage triggering. The applied forward voltage VAK is gradually increased beyond a point known as forward breakover voltage VBO and gate is kept open. So, see in this diagram, the voltage applied between anode to cathode is gradually increased from 0 beyond a point VBO. So, if it reaches the point VBO, then thyristor will get turned on. This turning on of thyristor from its off state is known as triggering. So, during this triggering, the gate should be in open condition. This method is not generally preferred because during the turn on of the thyristor, see, this is the point where thyristor is turned on, we are applying much more voltage. Due to this high voltage and high current, there will be a chances of huge power loss which may destroy the device. So, in order to protect the device, we should avoid this method of triggering. Next, thermal triggering. During forward blocking mode, most of the applied voltage appears across the reverse biased junction. So, we know that during the forward blocking mode, that is when anode is positive with respect to cathode, the thyristor is in the forward blocking state up to the breakdown voltage. The outermost junctions, that is 2 junctions, J1 and J3 are forward biased, but the inner junction J2 is reverse biased. So, this applied voltage will presence across the J2 and there will be a small leakage current. This leakage current will raise the temperature of the junction. When the temperature of the junction increases, it leads to decrease of the depletion layer. This leads to, that is, decrease in depletion layer leads to more leakage current and more junction temperature. So, these two processes, that is increase in leakage current and increase in junction temperature, these two processes are cumulative. Cumulative means if once leakage current increases, junction temperature increases. If the junction temperature increases, then leakage current increases. These two processes are going on cumulatively, one after another. So, due to this cumulative process, at some high temperature, depletion layer of this reversed biased junction J2 will get vanished and the device gets turned on. This type of turn on is not preferred as it may result in thermal runaway, hence it should be avoided. Next, light triggering. Light rays are allowed to strike the junctions of the thyristor. See here, this is the thyristor, this is the light rays. Now we are allowing the light rays to fall on the junctions of the thyristor. This falling of light on the junctions of the transistor results in increase in number of electron hole pairs. So, what is the effect of increasing number of electron hole pairs? Whenever the number of electron hole pairs increases, the conduction increases. Due to this, the thyristor is turned on. This type of triggering of SCR is known as light activated SCR or light activated triggering. Next one, dV by dt triggering. If the rate of rise of anode to cathode voltage dV by dt is high, the charging current through the capacitive junction is high enough to turn on the thyristor. So here the rate of rise of anode to cathode voltage is represented by dV ak by dt. If it is high, then the charging current is also high. Then this high value of charging current may destroy the thyristor. Hence, the device must be protected against dV by dt. So, this dV by dt protection for the thyristor is provided by the snubber circuits. Next one, gate triggering. Turning on of thyristor by gate triggering is simple, reliable and most useful method. When a gate signal is applied to the forward biased thyristor, thyristor will turn on. The forward voltage at which the device switches to on state depends upon the magnitude of the gate current. So this value of VBO will depends upon the magnitude of gate current. The relation between the forward voltage voltage and magnitude of gate current is inverse proportional. If the gate current is higher, then forward breakover voltage is lower. So these two are related by inverse proportion. Aspects to be considered for the design of the gate triggering. After thyristor is turned on, the gate signal should be removed immediately. So after triggering of the thyristor, the gate signal should be immediately removed. If we apply a continuous gate signal after turning on of the thyristor, it would lead to increase the power loss in the gate junction, particularly at the gate junction. And next one, no gate signal should be applied when thyristor is reverse biased. So in order to bring the thyristor from off state to on state, we are providing the gate pulse, that is known as triggering. But this gate pulse should be avoided in two situations. One is after turning on. After turning on, it should be removed. And the second one, the gate pulse should not be provided during the reverse bias conditions. Next, types of gate triggering. There are three types of gate triggerings: DC gate triggering, AC gate triggering and pulse gate triggering. DC gate triggering. A DC voltage of proper polarity is applied between gate and cathode. So we are applying a positive gate pulse to the gate with respect to the cathode. When this applied voltage is sufficient to produce the required gate current, the device starts the conducting. Drawbacks of this DC gate triggering. In this case, we are having two circuits. One is the control circuit and another one is the power circuit. So here both power circuit and control circuits are DC and no isolation between the two. So continuous DC signal has to be applied. In this case of DC gate triggering, we should continuously apply the gate triggering. So it increases the power loss. Next one, AC gate triggering. In this case of AC gate triggering, AC source is used for gate signal. In DC gate triggering, DC source is used, but in AC gate triggering, AC source is used for gate triggering. AC gate triggering provides proper isolation between power and control circuits. So in DC gate triggering, there will be an drawback. There is no isolation between control circuit and power circuit. But this AC gate triggering will overcome the drawbacks of the DC gate triggering. How it provides means by an isolation transformer. Drawbacks of this AC gate triggering: separate transformer is required to step down the AC supply. This is the main drawback of this AC gate triggering. There are two methods of AC gate triggering. One, R triggering, that is resistance triggering. Second one, RC triggering, that is resistance capacitance triggering. First one, R triggering or resistance triggering. This is the circuit for the resistance triggering. This is an AC source, and AC source is connected to the thyristor through the load, and anode terminal, cathode terminal, and gate terminal. So we should provide an gate pulse or voltage to the gate. So it is provided through the variable resistance R. So this variable resistance is connected to the cathode through the diode. See here, variable resistance R is used to control the gate current. So this is the path for flow of the gate current. So if we vary the value of this resistance, it will control the gate current. The magnitude of the gate current depending upon the value of R, because the gate current flows through the variable resistance. When the gate current reaches the value equal to the latching current of the SCR, then SCR starts its conduction. In this, the diode D is known as blocking diode because it prevents the cathode gate junction. See here, cathode gate. So it prevents the gate cathode junction getting damaged during the negative half of the supply. By considering that the gate circuit is purely resistive, so this is the gate circuit. In the gate circuit, we are having an variable resistance and diode. If you consider the value of the resistance of this diode is negligible, then this total circuit will be considered as an resistive circuit. We know that in case of this pure resistive circuit, the current and voltages are in phase. By considering that the gate circuit is purely resistive, the gate current is in phase with the applied voltage, and it has an drawback. We can achieve only maximum firing angle of 90. So this is limited to firing angle of 0 to 90. After 90 degree, we cannot get the trigger pulse. Next one, RC triggering. RC triggering methods provides firing angle more than 90 degrees. So it overcomes the drawbacks of the R triggering. During positive half cycle, the capacitor C is charged through the variable resistor up to the peak value of the applied voltage. So this capacitor charges the value equal to the maximum value of the supplied voltage. The variable resistor controls the charging time of the capacitor, and the gate current depends upon the voltage across the capacitor. The voltage across the capacitor will decides the gate current. When sufficient amount of gate current will flow in the circuit, the SCR starts to conduct. Very similar to the positive half cycle. During the negative half cycle, the capacitor is charged to the negative maximum value of the supply. Here also, the diode D1 is used to prevent the reverse breakdown of the gate cathode junction during the negative half cycle. Next one, pulse gate triggering. In pulse gate triggering, the gate drive provides single pulse periodically or sequence of high frequency pulses. This is known as carrier frequency gating. A pulse transformer is used for isolation. Advantages are no need of applying continuous gate cells, so the gate losses are reduced during the pulse gate. Advantages are low gate dissipation, small gate isolating pulse transformer. If the first trigger pulse fails, then following pulses can be used for the firing. It is used for inductive and also back EMF load.